I'd like to welcome everyone to the SDNS March webinar. My name is Elise Roberts, and I'm a member of the section on Statistics in Defense and National Security. And I am really excited to have Dr. Annie Booth speaking for us today. She is an assistant professor in the Department of Statistics at North Carolina State University. Her research focuses on surrogate modeling of computer experiments, including uncertainty quantification, active learning, Bayesian optimization, and reliability analysis. She completed her PhD in statistics at Virginia Tech, where she worked with advisors Bobby Gramercy and Dr. Higdon on developing deep Gaussian processes, or DGPs for short, as surrogate models. Dr. Booth's talk explores DGPs as a powerful tool for replicating and predicting complex computer simulations. Often used when physical experiments are impractical, DGPs improve upon traditional models by offering more flexibility and handling non-stationary data. Today, we'll learn how DGPs utilize advanced techniques like active learning and Vecchia approximation to make accurate predictions and improve efficiency, showcased with the DeepGP package for R. And with that, I will stop sharing my screen and hand it over to Annie to get us started.
Great. Thank you, Elise. I am happy to be here, and I'm happy to be able to reach this new audience. I'm going to, I'm not going to talk for like more than an hour. I'm planning for like 45 minutes. And hopefully we'll have time for questions and discussion and things like that. But within that short time frame, I'm going to try to give you an overview of like 3+ years of research. So it's going to be kind of a lot. But I hope that from going over things at a high level, I can pique your interest. And if you want to get into some of the more details or nitty-gritty of any of the topics I'm going to talk about, I encourage you to reach out to me or to check out our papers and things like that. So what I'm going to be talking about are deep Gaussian process surrogates for computer experiments. I'm going to break down all those words as we go along. I do want to shout out, most of this is work from my PhD. I graduated last year, and so I want to thank my advisors, Bobby and Dave, for their guidance through that process. And I've also collaborated on some of the work I'm going to talk about today with Ashwin Ranganathan, who is at Penn State University, and he's an aerospace engineer, and Andy Cooper, who was another graduate student at Virginia Tech with me at the time. So I am now at NC State. I've been there less than a year. So let's get going. The roadmap for my talk is super basic. I'm going to first tell you why we want to do a whole bunch of things, why basically every word in the title, why we may want to do it. Then I'm going to tell you more specifically what it is. That's going to focus on what the deep GPs are, and then how do we actually use them in practice. So very simple outline, why, what, how. That's where we are going today. So let me start with the kind of last words for my title, actually, why computer experiments. Computer simulations are valuable tools to supplement or replace direct physical experiments in a lot of different scenarios. If your physical experimentation is super expensive, maybe it's unethical to do something like studying the spread of diseases through population. Unethical to do a direct experiment on that. So we simulate what might happen under different situations. Maybe something is infeasible to experiment with altogether. So one of the examples I'll have later on is a simulation of a satellite moving through outer space. And we want to understand the friction or the drag that the satellite experiences. We cannot just, send up a whole bunch of different satellites and see which ones experience the least amount of friction, which ones, how the shapes affects their movement. We can't do that in the real world, just impossible. So computer simulations are our friends in these cases. Applications, I just mentioned a couple of them. I did add just for this talk. Applications include defense and national security. I will say computer simulations on this DNS type material is often less readily accessible and publicly available to the general population, but they do exist simulations of weapons, defenses, all kinds of things like that. So if you do have proprietary information on one of those simulations and you think you could get clearance to work with someone in academia, I would love to work with that. But because mostly what I work on are the applications that are more easily accessible to the general population like myself. So engineering applications, social networks like agent-based models, epidemiology like the disease spreading, or ecology like the population growth of fish in a lake, things like that. So why do we want surrogate models? Surrogates are just statistical models of computer experiments. We call them meta models because a computer simulation is like a model of the real world, and now we're putting a statistical model on that model, so hence the meta modeling structure. The reason we need surrogates is that they can provide predictions at inputs that we are not able to run through our actual computer simulation experiment. If those predictions come with appropriate uncertainty quantification, then they enable what I call downstream tasks. Things like Bayesian optimization, calibration to real experimental data, sensitivity analysis, and active learning, which I'm going to talk about near the end of my talk. These are particularly important when your computer simulation is expensive. Usually we're talking about computational expense. You may not be able to get a lot of data run through your computer model because maybe it takes days or even a week to get one single observation. Even on a supercomputer, these simulations are expensive. They can take a lot of computational time. So I do want to do a quick plug. If you're interested in surrogates and you don't quite know where to start, my PhD advisor, Bobby Grimsey, has written a textbook all about it, and this is freely available online. So I think that's a great resource to check out. Let's get into the meat of our talk, though, which is, okay, we have computer simulations to help us when we can't do physical experiments. We have surrogates to help us make decisions from those computer simulations. Why now do we want a deep GP surrogate? And to motivate why we want a deep GP, I have to start with regular GPs. So the typical surrogate model is a Gaussian process. It's nonlinear, non-parametric mostly, and it comes with analytic UQ. So to introduce that, the core assumption is just that your response variable follows a multivariate, normal, traditional Gaussian prior distribution. So I'm going to use the zero mean to simplify things, and all the work is going to be in this covariance function. You can think of this as a function of Euclidean distances. So if 2 points, xi and xj, are really close together, they're going to have stronger covariance between them than 2 points that are further apart. A couple hyperparameters, even though I said this is non-parametric, I've highlighted some hyperparameters in blue here. Tau squared just controls the scale. Imagine you took your response, you went from 0 to 1 to 0 to 100. You just need to scale up your covariances appropriately. This theta is a length scale. It's going to control how fast our correlation decays. So you can think of it as how wiggly your surface is. And this G is a nugget or a noise term. For the rest of this talk, we're going to assume that G is fixed to a small value. So we're only going to work with deterministic scenarios, although everything that I'm going to talk about is applicable to the stochastic sense. So this plot on the right, let's talk about this now. We're going to pretend that this is our black box computer simulation. You put in X and you get out Y, and that's represented by these red training data points. So our goal would be to fit a model to these points that can allow us to accurately predict the values of X's that we have not observed. So once we, assume this Gaussian process prior, we can condition on observed data like those red points, and we can get these posterior predictive moments, this mu star and sigma star. This is copied directly from any old textbook or the Wikipedia page for conditional multivariate normal distribution. So you can find these conditional formulas in a whole variety of sources. They're pretty well known. The key thing to take away from this is that we can get predictions at new locations, this curly X. Those predictions are also going to be normally distributed, and we can figure out exactly what the mean and the variance of those predictions is, as long as we know the hyperparameters of our covariance. So I just have a comment that we often will do maximum likelihood estimation for those, or we can do full MCMC sampling for those things like that length scale parameter. Those are both very common choices in this scenario. So now on the right plot, I am showing you a typical shallow Gaussian process fit to the data. If we had like a real live audience, I would ask for some audience participation. But for now, I'm just going to ask you to think critically. about how good is this fit right here. The blue is shaded region is showing our confidence interval. The dashed line is our mean. I would say it's doing a pretty good job at capturing the non-linearity in the left, right? The problem with this fit is that the variance is super overinflated on the right-hand side, right? Where we can see that this function's pretty obviously a piecewise function with a linear component over here on the right. But our Gaussian process model is not able to balance these two sides, the wiggly side where there's a lot of signal and the straight linear side. It can't reconcile the fact that these are two, disparate regimes, if you will. So what we would like is less inflated variance over here on the right. So let me show you a preview to motivate why deep GPs, because this Gaussian process is limited by what we call stationarity. So the true function that I took these red data points from, I'm showing you now in the left panel with this dashed line. This is the same fit of the GP I just showed you. Just want to formally tell you the stationarity is, the definition of stationarity is because that covariance function that everything really hinges on, that sigma in this Gaussian process, it is only a function of Euclidean distances between inputs. So there's no method for incorporating, maybe different regimes or stark switches and, piecewise functions cannot be modeled very well with a stationary Gaussian process. So preview, what does our deep GP look like, even though I haven't told you yet what it is and how we do it. The fit to this function looks a lot better. It does similarly on the left with the nonlinear portion of the space, which is great. I think that's an appropriate fit to that data, but it is much better able to pin down the UQ on the right-hand side. So the benefit of the deep GP is that it's more flexible and it can model non-stationary surfaces. I do want to shout out other approaches in the literature for how you can do non-stationarity with Gaussian processes. We could change our kernel to something more complicated. Non-stationary kernels are popular in spatial statistics, where your dimensions of your input space are pretty low, like 2, maybe 3. And they, for our purposes, they do not generalize very easily to more moderate dimensions, which we work with in computer experiments, think like 7 to 12, maybe. Another thing you could do is a treed or a local Gaussian process. So you could imagine with this piecewise function, we could chop it down the middle, fit separate GPs on each separate piece of that piecewise function. That is called a treed Gaussian process, and I will compare to that in a later figure. The tricky part of that is that you have to learn where the partition for your tree is. That can be really hard to do in higher dimension. In one dimension, we can eyeball it pretty easily, but imagine you have a 6-dimensional space. How are you going to cut your space up to fit these different Gaussian processes? And the other downside of that is that your Gaussian processes are then independent on your partitions or your tree nodes, and they're not able to speak to each other in a global sense. So deep Gaussian processes offer us this flexibility that we want while still being global all at the same time. They did originate in spatial statistics. Schmidt and O'Hagan had arguably the first deep Gaussian process, but they didn't call it that. The name deep Gaussian process came about in the machine learning community like a decade later, and it's recently, good names help things become popular, but also spurred by advancements in computation where we can actually do inference for these models now. Deep Gaussian processes have become really popular over the past couple of years for things like image classification, and we are now bringing them to the surrogate modeling computer experiments community. So what is a deep Gaussian process? A deep GP is just a functional composition of regular GPs. Now, there are papers out there in complicated ways that you can represent a deep Gaussian process. If you talk to a mathematician, they'll tell you a deep Gaussian process is like functional covariant. There are other ways you can represent it, but I think functional compositions are the easiest way to think about it. So let's direct our attention to the plot up here in the upper right of the slide for a second. I'm showing you x to y1, which is just a nice, smooth Gaussian process random draw. The blue-green color gradient on the bottom is just representing at this point the even distribution of x's that I started with, and I put those through a GP to get to y1. Now, if I take y1 and I feed that as an input to another Gaussian process y2, which I'm showing you in this small middle panel here, If I extrapolate, or if I kind of ignore y1 in the middle and I just look at x to y2, now I have a two-layer deep Gaussian process because it was formed by putting together two regular Gaussian processes. What is the point of all of this? Well, in the color gradient on the bottom, I'm now showing you the relative distribution of y1. And what's happening is that y1 compared to x is getting stretched out in the middle and it's getting squished on the edges. That's accomplished by this kind of, in the first panel, this steeper slope is effectively stretching and the flatter slopes on the edges are effectively squishing. So we can think of this latent y1 variable as warping our original inputs. Then we fit just a regular Gaussian process on the warped version and it can do really well. So now that we've got a framework, switch y1 and let's call it W, because in our heads, we're going to think of it as warping, right? W is this warping. So now I've got this formal definition of what is a two-layer deep GP. Well, X goes to W as a Gaussian process, and then W goes to Y as a Gaussian process. Together, those form our two-layer model. W can have multiple dimensions, so you can think of those as nodes if you like the machine learning nomenclature, but I like to think of W as just like a design matrix. So if my X is three-dimensional, then I've got a matrix that's like n by 3. I also probably want a warping that is n by 3 or three-dimensional to be able to accommodate that space. I think there's potential for dimension reduction through that warping, but that's a topic for a later time. So what we really want to do is we observe X, we observe Y. Those come from our black box computer experiment. We want to do inference on this likelihood without W. So we want to integrate out the unknown quantity. But this integral here is not tractable in general. There's no closed form to just integrate out the W. So what can we do? Hopefully we've learned in a couple of statistics classes that we can do two different things. Or there are two obvious choices. The first one is to approximate or optimize. Think of this like maximizing the likelihood, right? You don't know exactly what this closed form integral would look like, but we can find something we do know that's as close to it as possible. So we call this approximate variational inference. The goal of this is just to pick a posterior from a target distribution that you can understand and try to get it as close as possible to the unknown distribution that you really want. The difficulty with approximate VI is that this is way oversimplifying a lot of things, and it oversimplifies specifically the uncertainty quantification. It does not take into account the unknownness of W. So what we do instead is we're going to do MCMC posterior sampling. We are going to sample all the unknown quantities and then use all the samples, like burned in posterior samples, to give us full uncertainty quantification of all of our unknowns, because UQ is important for those downstream tasks that we want to do with computer experiments. So what do we do specifically? We do Metropolis-Hastings sampling for those covariance hyperparameters like those thetas, those length scales. Crucially, we do elliptical slice sampling for the latent Gaussian layers, which is W. W is just a Gaussian process. And then we iterate through all of these in a Gibbs scheme. I will say other works have come out that have done different things with these hyperparameters. So things like expectation maximization instead of the Metropolis-Hastings with very similar results. So the elliptical slice sampling of W is really the key. What you do with these hyperparameters is less important. So let's zoom in a little bit on what is elliptical slice sampling and why does it work so well in this model. This diagram I've put together here is showing you, just from a high level, the elliptical slice sampling algorithm. It looks pretty complicated, but I want to point out just a couple of highlights of this. So imagine this is one iteration of your MCMC sampler. First, you propose by sampling from the prior, and your prior on W is just a Gaussian process. So you sample from a Gaussian process. We know how to do that really easily. Then your proposal over here is a weighted average of your previous sample and that prior draw. Your acceptance, this is pretty typical. You accept just based on the likelihood ratio between your proposal and your last sample. That's pretty standard. But the key here is that if you don't get an acceptance, you don't quit. You don't like just repeat your old sample, because that could really get you stuck in some sticky chains. You instead just revise the weighting of your weighted average. So you're kind of shrinking this bracket. So if you're not getting acceptance, you are change the weighting so that it's almost more heavily weighting your previous sample, less weight coming from this prior draw. This allows us to kind of bounce back and forth effectively between nodes with this prior draw. It also gives us a rejection-free algorithm. So even though I say here, if rejected, it's not really if rejected. It's if you don't accept, tweak it and keep going until you get an acceptance. So every single sample or iteration should give you a new sample. What can this look like in our code? You don't get stuck in the weeds on this. I just wanted to show you how simple this can look like in our code. So you can create a function, sample W, that is really only maybe 10 lines of code here. You're going to get your log likelihood from your previous sample. You're going to draw from a prior, which is just a random normal draw. These lines of code are just for doing that kind of weighted with the elliptical angle. Then your W new is a weighted average of your last sample and your prior, and you accept based on this log likelihood ratio. If you don't get acceptance, you continue revising until you do. Now, I simplified this code hugely. I do not actually recommend you ever code in like a potentially infinite while loop. I would put like a failsafe in here, although I've never encountered it going through too many times. I have built all of this into an R package. If you look at my sample W function in the R package, it's actually much more complicated than this because it includes a whole bunch of different options. So I wanted to show you how simple this code can be, and then also show you that it's all wrapped in this nice R package. If you want to check it out, you can call this function fit to layer with your X's and Y's. It will do all the MCMC sampling for you. This trim function, you can cut off burn-in and then you can thin the samples if you want, and then you can predict for these xpredict locations, which is these nice 3 function calls. So I've shown you this plot here on the left before. This is the DGP fit to those red data points. Now I'm showing you this extra panel on the right. Each gray line here is an elliptical slice sample of W for this function. So what is each gray line doing? It has a slope at the beginning and then it flattens out near the end. So whether it goes up and down doesn't matter. All that we care about is the pairwise distances between those W's, because that's what feeds into our outer Gaussian process. So whichever way it goes, the slope here is effectively stretching the X's in the beginning and then squishing the X's in the latter portion. So that's what allows our function to accommodate this kind of piecewise nature, because it takes the X's where there's a lot of signal and there's a lot of wiggliness, it stretches them out, and it takes the X's where it's just the linear portion, it squishes them together. On that warped space, a regular stationary GP does really well. So that's all we're doing, building blocks, putting GPs together and learning what the warping should be by sampling it. So in 2 dimensions, I want to give you a quick visual. 1 dimension is kind of easy to conceptualize and plot. 2 dimensions is a little harder, but we can still do it. So each node of your latent layer is just a conditionally independent GP. In the bottom left panel here, I'm showing you a 2D function. It's called the G function. It's non-stationary. It's got these 4 stiff peaks and kind of these ridges and an X in the middle. The middle panels here in the yellow, orange, red surfaces, I'm showing you a sample of each node of W. So now we have a 2-dimensional function. So we have a 2-dimensional W. Each node is very simple in its shape. Each of these surfaces is pretty straightforward. It's just a Gaussian process conditioned on, that our X and Y data that I took from this function. Together, though, if we visualize those 2 nodes together, the right panel is showing us how a uniformly spaced X gets mapped through those 2 nodes into these red points, and it's effectively warping the space along the diagonals. So that's what we then fit our outer layer Gaussian process onto this warped version, and this gives us better predictions. So I do have results from this function in a paper if you want to confirm that this gives you better predictions, but I wanted to show you with this simple example just how the 2 nodes of W, even though they're just plain vanilla Gaussian processes, can give us effective warpings. So let's do a function that's a little bit harder though, because that one's still not too crazy. This function here on the left is 2-dimensional. It's called the Schaefer function. It's really non-stationary. It's got a whole mess of crazy stuff going on. So we fit both a deep Gaussian process with our elliptical slice sampling and a regular Gaussian process using MLE length scales to 500 training data points from this function. The box plots I'm showing you here are the prediction error on the left and the continuous rank probability score on the right. If you haven't seen that metric before, the CRPS just accounts for uncertainty quantification along with prediction accuracy. So RMSE is only how good is your mean. CRPS incorporates how good is your variance predictions that go along with the mean. Lower is better for both of these. So naturally on this non-stationary function, the deep Gaussian process can outperform the stationary typical Gaussian process. And I do want to say a lot of the test case functions that I use throughout, I pull from this virtual library of simulation experiments. Great resource. They have all kinds of test functions you can use. So how do we actually do these deep Gaussian processes in practice? I've actually told you a little bit of how we do the deep GPs. We do it in a fully Bayesian way with this elliptical slice sampling. But in practice, there's some other things that we need to take into consideration. So hopefully we can all reach agreement on this, but if not, we can debate this later on. But I argue statistical models are only ever as good as your data, right? So if your data does not reveal any non-stationarity, it doesn't matter if the surface is non-stationarity. If you don't have data in the right places or enough data, your model is not going to pick up on it. The data has to reveal what's going on in order for it to be useful to your model. So we built this flexible, deep Gaussian process so that it can handle non-stationary surfaces, but we need to make sure that the data we get from our computer experiment actually reveal the interesting stuff that's going on. So one way to do that is to just make sure you gather enough data, right? If you get enough data, if your computer experiment is not actually that expensive, you can do a space filling design, just get a lot of data, you're going to pick up on what's going on because you have enough data. So this works if your simulator is relatively cheap. The problem with this is that if you have a lot of data, you're going to hit these computational bottlenecks that happens with all Gaussian processes. So a Gaussian process uses this multivariate normal likelihood, which looks like this. It has a determinant of this sigma and it has an inverse of this sigma. This sigma matrix is n by n. So the cost of doing this inverse and determinant computation is n cubed. If your n is above a couple thousand, this can get really expensive. Now layer that into the Bayesian deep GP where we don't just have one of these likelihoods, we have two of them or more. You can go deeper than 2 layers, although I'm restricting myself to only talking about 2 layers for this talk. You have at least 2 layers, and now you're doing this in this Bayesian framework where every single MCMC sample that you get, you have to evaluate this likelihood multiple times. So these computational costs are really blown up in this Bayesian deep GP. So we need to do something to get around it so that we can handle large data sizes. So what have other people done? It is most popular in the literature to use inducing point approximations. So I have 4 references here. 3 of them use variational inference. One of them does Hamiltonian Monte Carlo, which is very similar to elliptical slice sampling, but I argue you could not code up HMC in 10 easy lines of R code. So we like the simplicity of the ESS. Either way though, all 4 of these references use inducing point approximations built in to their deep Gaussian process. Inducing points are like putting a bunch of knots in your space and kind of funneling your covariance matrix through those knots. If you don't have a lot of knots, this is going to be a really blurry approximation. If your knots are not in good places, it's also going to be really blurry. It's really hard to figure out how many knots you need. Most of the time, the default in these softwares is 100 because much more than that gets really expensive. But it's also hard to figure out ideal places to put them. And even if you do put them in ideal places, you're still getting kind of a fuzzy approximation. So I have encountered another work that uses random feature expansions instead of inducing points. I'm going to show you results from their software in a second. But we instead embrace Vecchia approximation. Before I tell you what Vecchia is, I want to show you a preview of how well it can work, right? Just kind of get you interested a little bit. So let me preview how well the DGP Vecchia approximation can work by showing you a plot that I have already shown you before with a couple new things on there. I have already shown you this red and yellow box plots just a couple slides back. I showed you the deep GP and the regular GP fit to 500 points from this Schaefer function. I didn't tell you at the time, but I was using Vecchia approximation under the hood with those models. Now I'm adding in these 3 other comparators. These are all different implementations of deep Gaussian processes that use different tools. So this first one uses variational inference with inducing points. Second one, Hamiltonian Monte Carlo with inducing points. Third one, variational inference, random feature expansions. All 3 of them are not able to perform as well as our Vecchia ESS implementation. And there's a couple reasons. First, I think Vecchia is giving us a much better approximation apparatus than these alternatives. Also, the ESS is giving us, I think, much more effective inferences. But all these things are intertwined in the software. It's hard to pull apart all these pieces that go together collectively into one software suite. But I do want to highlight, some of these deep Gaussian processes are so handicapped that they cannot even perform as well as the stationary Gaussian process in this scenario. So Vecchia approximation, we have found it to work really well, particularly in our DGP setup. Let me tell you a little bit more about what it is. The crux of this approximation is just this probability fact that any joint distribution can be represented as a product of conditional distribution. So for example, joint distribution of 3 y's can be broken down exactly, this is an exact equality, as these product of conditionals. If we wanted to do an approximation, we could take this first piece where y3 is conditioned on y2 and y1, and we could throw out one of those. We could just say, throw out y1, and now here only condition y3 on y2. If we threw out that one variable, so we're not conditioning on it in this component anymore, we no longer have exact equality, but we have something that's faster to compute and may be pretty close if we choose strategically what to throw out and where. So what we do with the Vecchia approximation is we just simply get our joint likelihood as the product of conditional likelihoods, where in these conditioning sets, so the CI, these are like conditioning sets, we throw out some things that we're conditioning on. So if we had 100 points, our 100th Y doesn't necessarily have to condition on all 1 through 99. Maybe it only needs to condition on 25 or so of those points. And if we choose them strategically, we use nearest neighbors, but I don't have time to talk about that today. We can get a really good approximation. What's going on under the hood here is really sneaky, is that this is really just inducing sparsity in the precision matrix. So you have a really sparse precision matrix, you can do really fast calculations with it. And Vecchia approximation was certainly not our idea. It has been thoroughly explored with regular Gaussian processes. Matthias Katzfis in particular has done a lot of work recently on these Vecchia Gaussian processes. We were just porting this over to the deep Gaussian process scenario. So don't have time to get into the details of this, but I want to show you the key takeaway is that Vecchia approximation makes things much faster. So in that same R package, you can use this fit to layer function. I have an input toggle here, Vecchia equals true. As a default, it's false, but all you say is, okay, trigger this Vecchia approximation. Then every calculation under the hood is going to use this approximation apparatus instead of doing those original full matrix inverses. It's not going to ever touch a full matrix inverse. You, as the user, won't see all those under the hood calculations. You will just see that your predictions and your MCMC sampling are much faster. So in this plot here, the blue points are showing training and prediction for Vecchia equals true implementation, and the black circles and triangles were training and prediction for the original unapproximated version. You can see the qubit costs versus the linear costs. So the linear computation allows us to go to data sizes that are much bigger. So new example, much bigger data. I'm going to show you this G function, which I actually showed you before in 2 dimensions. I showed you this plot here on the left. It's actually defined in arbitrary dimension. So I blew it up to 6 dimensions to make it a harder problem. I also found this on the virtual library simulation experiments. Great resource. Okay, in 6 dimensions, complicated surface, we need more data. So we bumped our training size up to 20,000 points. That data size would be totally infeasible to do without an approximation. It would just never finish. So we've done the sim study, same competitors, 3 competitors that are using alternative choices with deep Gaussian processes. In red, we have our fully Bayesian Vecchia approximated DGP, and then yellow is our Gaussian process competitor with the Vecchia approximation. So kind of similar trends, although now the disparity between the methods that are using Vecchia and those that aren't is growing. So the approximation apparatus that you choose can be almost even more of a significant choice than the model that you choose in this case, right? This surface is clearly non-stationary. A Gaussian process cannot do as well as a deep one, which we see from the red versus yellow. But your deep model is not going to, be up to standards if it's using a bad approximation under the hood. So that's our takeaway from this. Let's get back to where we first kind of started with this. How do we do these things in practice? And I said, one of the things you can do, get a lot of data, and then you'll pick up on what's going on, right? If you have a lot of data. So 20,000 points in 6 dimensions, cool, good to go. It's probably not feasible with a lot of computer simulations to get a lot of data. So now we're going to segue to what if your computer simulation is expensive and you can't get a lot of data? You can do this thing called sequential design or active learning. So we're going to deploy this kind of greedy algorithm if we know from the start that we can't get a lot of data from our computer model because it's expensive. So we're looking at a very limited budget. What we want to do is make the most out of every single input that we choose to run through our model. We don't want to just waste them because they're expensive. So we want to make the most of it. So if your simulator is costly, you need to do, or you should, I recommend, you should do this kind of loop to collect your data. So you start with a small initial design. Often this is like an LHS or something space filling or random. You fit your surrogate model to it. You use your surrogate to tell you which inputs you should run next. So this is selecting your next design location. You say, where will we get the most bang for our buck? Those inputs, then you run it through your simulator, you augment your data, you update your surrogate, and you go through this feedback loop until you've exhausted your budget or your surrogate has saturated or some kind of stopping criteria. The beefy part of this that I've a little bit glossed over in this diagram is this box here. How do you select your next design location? Well, the common thing to do is we actually choose this xn+1 by optimizing an acquisition function. And your acquisition function is supposed to quantify the utility of a certain input with regards to whatever your objective is. If your objective is to optimize the surface, then your acquisition criteria should focus on getting you to the optimum, right? I'm going to talk about that in a second. If your objective is instead to maybe find a level set or identify a contour in the surface because you want to do, some reliability analysis, then your acquisition function should target learning a contour, right? So we're going to get to some brief examples of both of those next. The first one I'm going to talk about, though, is if you don't have any general objective and you just want to maximize your learning as you go, just in general, we want to learn the most about our surrogate, get the most accurate predictions with the lowest variance. That's what we're going to touch on first. But regardless of what your goal is and what your specific acquisition function is, you have to optimize that function in order to pick the best one. You want the input that gives you the maximum value of this acquisition function. That can be really hard to do. What a lot of people do is they do this multi-star numeric optimization, something like BFGS, to try to find, the optimum of this acquisition function surface. That is not feasible with our deep Gaussian processes because first, we don't have any gradient information yet, although maybe that's an avenue for future research. We don't have gradient information. We also have this big, hefty MCMC model that's carrying around a lot of elliptical slice sampling iterations with it. And so if you're doing this kind of numerical optimizer where you're sequentially evaluating a whole bunch of different inputs to try to get these auto diffs and multi-star, and it's just not feasible. So what we do instead is we pick candidate locations. We come up with some candidate X's. We can evaluate the acquisition function at those locations in parallel pretty quickly for our deep Gaussian process. And then we just pick the candidate that gave us the best value. Okay, so let's revisit. If you have just a general goal of I want to maximize my learning, I call that variance reduction. Your goal is I want to reduce my variance across the whole space. You can do this with this criteria such as integrated mean squared error. So here I'm using candidates. This is a function that's built into the DGP package. You just spread some candidates out in the space, evaluate this integrated mean squared error. You choose the candidate that gave you the biggest reduction in variance and you repeat. So Here's just a quick example of a 7-dimensional simulator of a satellite moving through outer space, or low Earth orbit, technically. We started with 100 points, and then we used this IMSE criteria to sequentially select 400 new acquisitions until we had a total budget of 500. Our 2-layer deep Gaussian processes are in the red, blue, and brown, and they all achieved better predictive performance than the stationary 1-layer Gaussian process in green, or the non-stationary treed Gaussian process, which is this purple alternative, which is non-stationary, but has this extra challenge of having to figure out where to partition the space, and then it's fitting independent GPs on the partitions. So those handicapped it in this scenario. So I do encourage you, if you're interested in more on the variance reduction, to check out our paper on the active learning with the DGPs. I just wanted to show you a taste of what you can do with that. What we realized, though, when we were doing this is that if your acquisition criteria is more complicated, like you're not just trying to, reduce variance, learn the whole space as best you can. If you're trying to do something specific, you need to be more strategic with where you place your candidates. So in this example, we just used a Latin hypercube space filling design to spread out candidates and choose some. That works well in these simple kind of variance reducing cases. But if we wanted to segue into a Bayesian optimization or a contour location, we had to be much smarter with how we chose these X candidate locations. So what we came up with is this thing we call it tricans, or triangulation candidates. So the idea here is you need to be strategic with where you're putting your candidates. You don't just want to randomly spread them out, especially in higher dimensions under limited budgets. It's not going to work great for you. So what we did is we figured out that we can use this Delaunay triangulation of your existing design. So in the right panel, the open circles are just representing a hypothetical training design or an initial design in 2 dimensions. So that's, imagine that you've already collected data at those black circle locations. Now you need to propose candidates to choose a new X. And your new X is going to be limited by only these candidate locations. You're going to pass it through whatever acquisition function you want, choose the best one. So what we do is we triangulate the existing design, which is represented by these solid lines. We form this triangulation where you have no overlapping triangles. You basically partition the space in this way. And we do use our package that has already coded this up in a fast optimized way with C under the hood to get this triangulation. And then we propose candidates as these red diamonds at the center of those triangles. So these candidates, with relation to the designs we've already seen, or the design points, the open circles, they're spread out. They're infilling places we don't already have data, which is where your acquisition functions are most likely to be optimized. The other thing we do is that we put candidates around the outside of this. So we take the outer edges and we extend candidates out before they reach the boundary of our space. We call these tricans, triangulation candidates. And we have found in a variety of settings that these work better than just regular space filling candidates. So here's an example of a Bayesian optimization scenario. So our goal is to minimize the function with as few evaluations of the function as possible. So in this lower left panel, I'm showing you the Levy function. This is what it looks like in 2D. We bumped it up to 5D for this scenario, but it gives you kind of an idea of how complicated it could be. We started with 12 points spread out through the space, and then we did this Bayesian optimization. Our acquisition criteria here is expected improvement, which is built into the R package as well. You can give it candidates and say calculate EI. And then you select the candidate that gave you the biggest expected improvement, and you keep going. The plots I'm showing you now here in the center are showing the best or the most minimum value observed at that point as we went from 12 to 75 points. The dashed lines are both versions that use tricans versus the solid lines, which use LHS space filling candidates. And the blue is a deep Gaussian process compared to a treed Gaussian process in the black. So this is just an example showing how using strategic candidates like the tricans outperforms space filling candidates with both models, but also using the appropriate model like the deep Gaussian process for this surface outperforms other non-stationary models. So we're able to achieve lower values with fewer evaluations from our, in this case, test function, but in the real world, this would be your expensive computer model. Okay, so lastly, I want to touch on this contour location scheme. I don't have much time, but I want to give you a brief example of what you can do with this contour location. So say that instead of optimizing your function, you wanted to identify a level set in the surface. I've got an example here in the lower left panel. This is a heat map of a two-dimensional function. I found all of these on this virtual library. Super good resource again. This two-dimensional function is really non-stationary. It's flat in the four corners, and then in this ridge in the middle, it has a really steep, stiff, like peak in this x. So the contour of this function that we want to find is identified by the blue line. So our goal is with as little data as possible, identify this entire contour, this whole level set, because the region in the white yellow in between those contours is later we're going to consider those failures. And we want to classify like the probability of failure down the line. So we need to know where the whole failure region is. What we did is we started with 50 random points, and then we went up to a couple hundred acquisitions. We used something strategic here where we used tri-cans as our candidates. And we also used our acquisition function was actually a strategic combination of entropy and uncertainty. So I'm going to not have time today to get into this Pareto front idea, but we basically chose the candidates that gave us the biggest entropy, which is classifying how uncertain you are and whether you're a pass or a fail, and the highest posterior variance. And the way we did that was by choosing the Pareto front of those two variables. But aside from the details of that, the key takeaway from this is that with a deep Gaussian process, I'm now showing you the DGP in this green teal color, you can get better performance in this scenario, our performance was the sensitivity in classifying failures. So how well are we predicting this failure region? We are getting better performance than our stationary Gaussian process competitors. In this case, the orange line is the exact same as the green line. It used tri-cans and this Pareto front acquisitions, but the only difference was that it was a stationary GP instead of a deep GP. So the difference between green and orange is showing you how effective the deep Gaussian process model, which is necessary for modeling this non-stationary surface, can be with these different kinds of sequential designs. On the right, I'm just comparing the end of these box plots. So the lines are median. So I'm showing you the end result over a bunch of Monte Carlo repetitions compared to if we just did a static space filling design from the start. So if we didn't do a sequential design in any way, we just did a static space filling design, same budget, we are getting much, much worse sensitivity predictions from those static designs. So key takeaway. Sequential designs are important if you have specific objectives you want to accomplish and you don't have a lot of data, you have a limited budget. Using the right model, like a deep Gaussian process, if your service is non-stationary, can be really important, but also using strategic candidates and smart acquisition criteria all come into play to get you the best results. So I want to open the floor to questions or discussion. I do want to comment. I've mentioned this throughout the talk, but all the code I shown you was wrapped in this DeepGP package, which is available on CRAN. And every single plot I showed you is also provided in this deep Gaussian process like repository that I have on Bitbucket. You could reproduce all the examples, all the plots, everything from there. And if you don't want to chime in with a question now, but you come up with a question later, or you try out this R package and later on you encounter something, feel free to shoot me an email after the fact. So that's what I've got for now. Thank you all for listening.
Thank you, Annie. Is there anyone on the line that has a question?
Oh, I forgot to say this at the start too. I used to be named Annie Sauer. So
Yes.
I was gonna say throughout, I should have said this at the beginning. I was named Annie Sauer. So, and when you see any of my previous works with the name Sauer, that was my work. And last year I got married and I changed my name to Booth. So those are my more recent works.
Oh, thank you for the clarification. Sorry about that. I should have asked that before.
No, that is okay. As time goes on, I forget to say it. At a certain point, I won't need to say it anymore, probably. So.
And for our audience members, a recording from today's webinar will be posted to the SDNS YouTube channel at AMSTAT, SDNS, and I will send out an announcement through ASA Connect and the SDNS website when it becomes available. And
oh, can we ask questions?
Oh, go ahead. Go ahead, Parker.
Yeah, so is there any, I think you skimmed over a little bit, but is there any like high level advice for how many latent layers I should choose, as well as I think you call it the number of nodes? Like any suggestions on like, because I could imagine things get really complicated with really high dimensions and lots of latent layers really fast. But is there any gain to using those?
That is a great question. So there's two things at play here. How deep do you go, which is how many Gaussian processes do you like compose on top of themselves? And then how wide do you go? So that's, I guess, kind of like neural network speak there. So let me address the first one. How deep should you go? I have tried everything in 3 layers. So you have like 3 Gaussian processes put together, and you have a like 2 latent layers. You have to elliptical slice sample. And in the R package, you can try out 3 layers. There's a fit 3-layer function. From my experiences with the computer experiments and the scenarios I've been working in, I have not ever found a benefit to going past 2 layers. I think that what we're working with is just surfaces that are not like that crazy. You know, they have some non-stationarity, but they're not like pathologically crazy. In machine learning applications where they're doing things like image classification, I have seen papers that go as deep as 5 layers and they find some benefit to it, but they're doing variational inference and different approximations. They're doing things very differently. So in this fully Bayesian elliptical slice sampling framework, I have seen that 2 layers is almost always your best option. 3 layers is almost just a whole bunch of extra computation for almost no payoff. So my recommendation is 2, stick with 2. Then how wide should you go? How many nodes should you have in your latent layer? My base recommendation is match the dimension of your inputs. So if you have 7 inputs, you should start with a 7-dimensional W. I did try an example, let's see here, where I varied how many nodes were in the latent layer. So this was a 7-dimensional input space. So the 7 nodes had 7 W's to go along with those 7 columns of X. But I also tried out 5 and 3, and we saw that in general, the 7 did the best, but there's almost these diminishing returns as you go. So I think an area for future research is, you know, the potential for dimension reduction, right? Like maybe there's some kind of lower dimensional warping that would accomplish what you want. Haven't investigated that yet. My recommendation is match the dimension of your inputs as a safe bet. Really good question.
Yeah, very good question. Any more questions? Oh yeah, go ahead, Dirk.
Hi, thank you. Very interesting talk. Is there any insight for the failure of the inducing point methods? I mean, you compared with textbook well-established inducing point methods, and so they perform even worse than a shallow GP. So is that are these particular features of the test function that you are looking at, or could you sort of share any insight on why they fail? Given that these are sort of well-established methods, I found it surprising that they are even worse in performance than the shallow GP.
Yes, super good question. So inducing points are super popular. They have been around for a long time and they are well established, like you said. So in our comparisons, the problem with doing these inducing point comparisons is that they're all intertwined with a lot of different choices. Like all 3 of these first competitors here had different inferential apparatuses. They had different methods that they made. Because these DGP models are complicated, you actually have to make a lot of modeling choices, which is one of the benefits, I think, to our package, is that we made a lot of those choices as simple as we could. And so you can just use them with the defaults. But so my answer is twofold. I think part of it is that the inducing points are so intertwined in the software with other choices, it's really hard to pull apart. So if we wanted to do a fair comparison, we would really have to code up inducing points with the elliptical slice sampling with everything else the same. I don't want to spend the time to do that because I don't think it will pay off. The inducing points are really like confined by how many inducing points you have. The problem is that the cost of the inducing, it's cubic with how many inducing points you have, whereas the Vecchia approximation is linear with your conditioning set size. So to get good inducing point approximations, you need, I think, a lot more knots. And under the hood, almost all of these software have 100 as like hard-coded 100 inducing points. That's it. And it's not very easily user adjustable. And so that is a pretty steep handicap, especially in multiple dimensions. 100 inducing points just doesn't cut it. But if you go higher than that, it's way too slow. It's cubic costs. So I think Vecchia approximation is superior to inducing points. Like that is just my opinion. I think it's going to take over the next, decades. And we're not going to really see inducing points anymore. But a fair shot-for-shot comparison would be helpful to, make that like less of an opinion and more of a fact.
Okay, thank you. So you reckon it could also be an interaction between the inducing point approximation and the variational approximation, because you really have sort of a different sampler, the elliptic slice sampler might contribute to the better performance of the Vecchia approximation.
Yes. I think the fairest comparison would be the HMC, which is Hamiltonian Monte Carlo, because the HMC and the elliptical slice sampling are both doing this Bayesian MCMC. So the fairest comparison we have now is green to red, because they're both doing MCMC, inducing points in green, Vecchia in red. But even that, it's not totally fair. There's different modeling choices under the hood.
Okay, thank you. Thank you.
Great. Thank you, everyone. Thanks for coming. I appreciate it. Thanks for the invite, Elise and Parker.
Of course. Thank you to everyone for attending today's webinar, and great talk, Annie. I'm so glad we could have you on today's webinar.